In this lecture we will consider examples of the expressions of an homomorphism that we described in lecture 9.2. Let's start with the axial symmetry about the coordinate axis. This is a map from R2 to R2 which depends on a line axis L. Let's first consider the case where L is the y-axis. Then in coordinates, the axial symmetry is defined to be the map that sends the pair x1, x2 of coefficients, therefore a generic element in the domain R2, to the following element. It is negative x1 comma x2, so it acts in the second coordinate as the identity, and in the first coordinate it just multiplies by -1. Now, since both components of SL are linear, you see the first component takes the pair x1 x2 and returns negative x1, so it just operates linearly on the coefficients, and the second component is just a projection on the second component of x1 x2. By what we said the previous lecture, we know that this fact implies that SL homomorphism. So see lecture 9.2. If L is the x-axis, SL is defined to be the map that sends x1, x2 to, this time x1, the first coordinate is left unchanged, and the second coordinate is multiplied by -1. So let's see graphically the images of some points of this map. I remind you that in the lecture 0.2 we considered the visualization of maps. In this case, the map goes from R squared to R squared, so we cannot draw its graph because it would be embedded in R4. And hence, we just have basically one way to represent graphically the action of the map, and that is to pick some points or some subsets of R2 and see what's the image of these subsets. In this case, let's pick a generic point P with coordinates x1 and x2 and see how the map operates on this point. We are looking at the symmetry, the axial symmetry about the y-axis, and you remember we just said before that about the y-axis it sends the first coordinate in its opposite, and the second coordinate is left unchanged. Therefore, if P has coordinates x1, x2, it will be sent to the point with coordinates negative x1 and x2. And this is its image for any point in the plane. If we start from a point here on the left-hand side of the plane, they will be sent the other way around, so from the negative part of the x-axis to the positive part of the x-axis. What about Sx, which is the axial symmetry with respect of the x-axis? So in coordinates, the action of the map is described by this equality. Basically, it changes the sign of the second coordinate. So if you start from a P of a coordinate x1, x2, it will be sent to x1 again and negative x2. So it just flips the point around the x-axis. Notice how easy it is, if we have the expression in coordinates of an homomorphism, how easy it is to find images of any numerical vector that we might have in the domain. So if we wanted to find the image of, I don't know, 3 square root of 2, well, from this formula we immediately see what the image is, just plugging in the numbers in the expression. Let's see now what it amounts to express these axial symmetries by assigning the image of a certain basis of the domain. That was the second way we could communicate, or we could find linear applications that we mentioned in lecture 9.2. We want now to express Sx and Sy by determining their actions on some basis of R2. We have complete freedom of choosing a basis. So let's be clever and choose one on which Sy, for example, acts in a simple way. Since Sx and Sy are simple homomorphisms, it turns out that any basis of R squared will do it. Indeed, let W equals to W1, W2 and Z with coordinates Z1 and Z2 be any basis of R squared, seeing R squared as a domain in this case. Then Sx is defined to be the unique homomorphism sending W to the following vector W1, negative W2 and Z to Z1, negative Z2. And Sy is the unique homomorphism sending W to negative W1, W2 and Z to negative Z1, Z2. We don't see any reason to pick one basis rather than another, just because we have an easy understanding of the homomorphism on any basis. We discuss now a generalization of the axial symmetry of point 1, which is the axial symmetry about any axis now, not coordinate axis. Let L be any line in R squared and consider the map geometrically defined as follows. We have a line L in R2 and we have a point P, and we describe now how to geometrically construct the image of P. So we project orthogonally P on the L axis. So the distance between P and the axis is defined to be the distance between P and its projection on the axis. We take the line, that is the normal line, to L passing through P, and at the same distance A from the projection of P to L, but on the other side of the line L, we find a unique point. Which we'll call SL of P, and this is the image of P through the axial symmetry about the L axis. Okay, first notice that if the zero vector is not in L, then SL is not going to be linear, since the image of the zero vector is not going to be zero, is not going to be the zero vector. Notice in the axial symmetry, the only points that are left fixed are the point of the L axis. For a map to be an homomorphism, it is necessary that the zero vector is being sent to the zero vector, and while this has been shown in lecture 9.1, we want to make sure that the L axis will pass through the zero vector, so will pass through the origin. That way the zero vector will be left fixed, and this necessary condition is satisfied. Of course, it's not sufficient, but one can prove that any axial symmetry about any axis passing through the origin is indeed a linear map. So we will have to assume that the zero vector belongs to L, then SL is linear, but it is too complicated to express it in coordinates at once, in general. We will express it by determining the image of a cleverly chosen basis of the domain, since the image of a randomly chosen basis takes too much effort to compute. Unlike the previous example, in this case, if we just pick a random basis of the domain, finding the image is rather complicated. We have to make these geometric constructions and use trigonometry in order to see the images of these two randomly picked linearly dependent vectors. While we can make our life much easier choosing a specially designed basis for this situation, this linear map. Let WZ be a basis of the domain where W belongs to the line L and Z is perpendicular to L. Then we can see from the definition of the axial symmetry that the SL of W is W because belonging to the axis it is left unchanged. And the image of Z, it just gets multiplied by 1, so Z goes to negative Z. In order to see this, let's check out this picture. We have the x and y axis, we have our L axis that passes through the origin. And we take W to be just any point in the line different from, of course we want W and Z to be a basis, so neither of them will have to be the zero vector. So we pick a non-zero vector in the line L, W, and then we pick any vector Z that is orthogonal to W. Mind you here that we have not covered the analytic geometry part of the course. Therefore here I have to spend few words in describing what we mean with perpendicular vector to another vector. We have been drawing vectors just like points. However, in order to show what the angle of two vectors is, it is always better to connect the points to the origin with a segment. Because by definition of angle is defined for some regions that are bounded by rays starting from the same point. Therefore, in this case, we can visualize what the angle between W and Z is once we connect Z and W to the origin with a segment. This picture shows a vector Z that is clearly orthogonal to W because this angle is right, and I could have taken any vector on the line connecting Z with the origin as long as it was not the origin itself. So any vector on this line would do it, so just pick one and call it Z. Obviously W is left unchanged and Z is being sent to the vector with the same distance as Z from the origin on the other side of the line. Therefore, the image of Z is going to be negative Z. So the opposite of Z, the vector that has the opposite coordinates as the ones of Z. The fact that SL of W is W and SL of Z is negative Z would not be true if I had chosen vectors in a different way from the one I've chosen here. We have a particularly easy description on just these two vectors of the map SL. So let's go now and see the procedure to express the SL by means of these bases. The expression of SL through the basis WZ is, so W goes to W and Z goes to negative Z. I remind you that determining or expressing a map means communicating something in such a way that the reader or the listener is able to find the image of any element of the domain. That means having communicated or having described a map. To find the SL of V for a V in R squared, a generic vector in R squared, so finding its image, we need to go through the following steps that have been explained in lecture 9.2. So the first step is express V as a linear combination of W and Z and find its coefficients. So let V be equal to alpha times W plus some number beta times Z. The image of V through SL is then forced to be the following: alpha times the image of W plus beta times the image of Z. It means that SL of V must be equal to alpha times W minus beta times Z by linearity of SL. Step A involves solving a system in two unknowns, A, alpha and beta, and two linear equations. It is an equality of two vectors in R squared in two unknowns, alpha and beta, and the two vectors in R squared reduce to two equations, one for the first coefficient of the vectors and the other equation for the second coefficient of the vectors. This for every vector of which we want to know its image. So as I anticipated you in the previous lecture, the expressing a map by setting the image of some basis, it involves a longer procedure for finding images of any other vector in the domain than having it expressed in coordinates. In coordinates, I just have to plug in the coefficients of the vector I want to find the image. On the other hand, if I just know the image of a basis of the domain, I have to first find the expression of the vector in function of this basis, and that involves the solution of a system of linear equations. Therefore, I'm going through many more computations than just having it expressed in coordinates. However, in coordinates, I cannot tell you right now the expression of SL, but as image of a basis, I've already done it. It's very simple. It was described in part B of the two steps before. So this is an obvious example on how one should proceed. In order to find some homomorphism, it's okay if one chooses a particular basis that is cleverly determined in function of the problem that one is facing. In this case, we deeply use the fact that the axis we were using for the axial symmetry was L and not another axis. We have chosen the basis very much depending on what the axis L was. If L were expressed in coordinates, SL of x1, x2 would be determined by the following equality. So I would have SL1, the function SL1, and then SL2, that are the two coefficients of the images, and I would have just to plug in the values a and b for x1, x2 if I want to find the image of V. In the next lectures, we will learn a method to pass from the basis expression to the coordinate expression.